We now start with what is a forcing extension of V by Neil Barton.
Great. Well, thanks very much, and thanks everybody for coming. Looks like it's going to be a great program. It's very nice to give one of the early talks. I thought I'd give a suitably sort of controversial title by turning up to a set theory conference as a philosopher and telling them what a forcing extension of V was, as if they didn't already have some idea of that. But really, this is a sort of interesting question that occurs at the intersection of philosophy and mathematics, where you've got philosophical conclusions being drawn from a lot of heavy mathematics. So here's where I'm going to start. So a lot of debates in the philosophy of set theory seem to have reached, and this I'm not going to argue for, I'm just going to say this, but they seem to have reached something of a sticking point. So there tends to be a lot of just intuitive disagreement about the philosophical role of model theoretic construction. So people who propound multiverse views tend to think, well, this is very indicative of the fundamental subject matter of set theory, and those that think there's one universe of sets tend to think, no, we can interpret this all as substructures, and this doesn't really threaten my view. So because there's this sticking point, I think a really natural methodology is to see how each view can fill out their own position and see if we get any foundational fruits that fall out of this. So if you fill out universism, exactly how they're going to try and do the things they want to do, what happens, and if you fill out multiversism, what happens then? And there's been some really good work in this. So a good example on the multiverse side is stuff like the work on the modal logical forcing, things like that. Okay, but I'm going to be interested here in universism and something that universists try and argue. And what I want to do is I want to accomplish three main aims that I'm going to give you a sort of sketch of things, and we can maybe discuss it a bit more in the Q&A. So I want to convince people that, firstly, extant interpretations of forcing extensions, possibly where the symbol V is used in forcing arguments for the universist, there's an extant challenge there in some of the work they might want to do. And secondly, I'm going to argue that you might, given certain philosophical interpretations of how we should talk about proper classes, you might be able to at least motivate something stronger than just a predicative class theory. You might be able to get something like MK. And then finally, I'm going to argue that this allows the universist to make use of resources of forcing arguments where V really does denote V, it denotes their whole universe. You can code things up within the class theory in a certain clever way. Okay, so I'm just going to make a few more introductory remarks, and then I'll go through these classical interpretations of forcing extensions. I'm sure people are pretty familiar with this. And we're going to talk about a way you might represent forcing through Boolean ultrapower, which again, I'm sure lots of people are familiar with, but I will go through. I'll then go through drawbacks for this way of representing forcing on the universist perspective, but draw a kind of philosophical lesson from that. And then finally, I'll just show how you can, with a pretty strong class theory, interpret claims concerning V and forcing extensions. And then I'll finally just make some concluding remarks. Okay, so if you're not keen on the philosophical literature, you might be unaware of these two views, but this seems to be really one of the central debates in the philosophy of set theory at the moment, is how many universes of set are there, or is there a maximal interpretation? And universism says yes, and multiversism says no, there's no such universe, rather the universes of many. I mean, each of these views is really a family of positions. So, for instance, you might think, if you're a universist, that the universe is indefinite in some sense, so you still don't get the bivalence of independent statements. Solomon Pfefferman has a view something like that. And multiversism, again, depending on what you take to be well understood, you'll get different views out. So, for instance, Cy Friedman thinks that the natural numbers are well understood and then just has lengthenings and thickenings. And then Joel Hamkins thinks that you can have perfectly well non-standard numbers in a model of ZFC. Okay, good. So there's a salient challenge for the universalist in that you have this vast zoo of set theoretic models. Some of them satisfy CH, some of them don't, some of them satisfy diamond, some of them don't, and so on and so on. Now, a natural question to ask if you are a universalist is, look, can you get out more than ZFC? If you're a universalist who believes that every sentence is either true or false, can you provide reasons to accept an extension of ZFC that will settle some of these independent sentences? This fits very nicely into the universalist picture. And a lot of interest has been generated here about specific axioms. So good examples are people like Peter Koellner discussing the relationship between axioms of definable determinacy and large cardinals. So if you have large cardinals, you can prove things like PD. And the other way around, if you assume definable determinacy, you can get out inner models with large cardinals. And what the justificatory story to be told there is a really good question. But I want to just take a step back from that and say, okay, you can have those discussions about specific axioms, but what resources can you use in proving facts about V, and also formulating new axioms that we can then try and assess for truth. And this is interesting. I'm hoping that this will be able to open the door to a new kind of discussion for people inclined towards universalist mathematics. Okay, so here's just two examples of principles we might want to look at. So the first is the inner model hypothesis that Cy Friedman, along with Karen Antos, Radek Konzek, and Claudio Tonello have discussed. So this just says that, well, you can't see it now, but if you have V, and you can thicken it out to VG, if something's true in an inner model of the forcing extension, then it's already true in an inner model of V. This has some interesting consequences. In particular, you get anti-large cardinal features out of this sort of principle. And it might be one that, as a universalist, you want to consider when you're, when you're looking at new axioms, but you can't do it because you obviously can't talk about forcing extensions of V. V is supposed to be all the sets there are. Okay, and the other is, well, I'll leave this up here for now. The other is essentially generic embeddings. So if you have V and you thicken it out to VG, you might want to look at, well, if we take, this is V, this is VG, if we take some inner model of VG and we embed V in here, you can get these nice little embeddings, and the critical points here can be very small. So this can be as small as, for instance, omega 1. Now, the universalist isn't going to be interested very much in what goes on outside of V, because they don't really think that exists. But if they can use this sort of construction to figure out properties of things in V, then that's interesting for them. This gives them a new resource to talk about what goes on inside V. Okay, good. I mean, the details here are not important. It's the general philosophical idea that I'm interested in. Okay, so what are I'm going to sort of pretty quickly scoot through the classical interpretations of forcing extensions. Well, how do we do it? Well, we could use countable transitive models, and this is all familiar. So if I just do it up here, if you have V, and you just look at some tiny little countable piece of V here, and then, well, if this is V going off here, you've got all the generics you could ever dream for in there. But, this doesn't get anywhere near all the things you wanted to talk about with generic embeddings or the proper class models of the inner model hypothesis. The objects are just way too small, and so for proving facts about those objects you wanted to talk about in V, it's not going to do the work. Boolean valued models is another option, so you provide this Boolean valued description of V. Okay, so two problems I see for this. Well, one is that it's a little clunky in that the reasoning is not too valued or combinatorial really, especially with generic embeddings. We want to look, how are we moving the ordinals here? How can we bolt all the stuff in these models together? And it doesn't really respect that. It's just this non-too valued description. More importantly, though, it's really unclear how to deal with class forcing here. I mean, it's not necessarily impossible, but if you have your partial order, in V, and you want to look at its Boolean completion, and this thing is class sized, if you're a universalist, you've got nowhere to go out the top, so class forcing is a problem. Finally, you could use the forcing relation, so look at the individual forcing conditions and see what they tell you would happen in the ideal extension. But I wonder here if, this is a bit more speculative, but standardly, people have been very concerned with definable class forcing, so I'd like to know if there's any particular reason why we should always restrict cases where the forcing relation is definable. Let's look at all sorts of, weird and wonderful extensions and see what we can learn. Okay, so I'll just quickly take you through the Boolean ultrapower, and this pops up in the work of Hamkins and Siebold. So it's really just an extension of the normal Boolean valued model framework. The important thing to note, though, is that so you start with a class of V names, and then you take an ultrafilter on the Boolean algebra. It does not need to be V generic. It's really important to note. So if you have, normally when you're doing forcing, have your V and you need to take something generic that intersects all the dense sets, you could just take any old ultrafilter in V. And you define, the usual sort of equivalence relations you do with ultrapowers. So you say that two names are equal according to the ultrafilter if their Boolean value is in the ultrafilter. And similarly for, this should be a membership sign. If they're members, if one being in the other is in the ultrafilter. And similarly, you can add in a predicate for the ground model to represent the ground model. Okay. And then you take the restricted equivalence classes, massaged by Scott's trick, and you get two real structures of interest. The first is the Boolean ultrapower, which is this embedding into I'll just sort of give the philosophical upshots, and then you can see the kind of formalism. Put it back up. So what we do here is we take V and we embed it into what turns out to be an internal model with this JU. See in a minute that this picture's a little bit simplistic. And then you can then look at the canonical name for the generic filter turns out to be the V-check U generic for the image of the algebra. So you effectively can look within V at this kind of definable simulation of what a forcing extension of V would look like. And then we might say, okay, well, we can use that to interpret our forcing. And then maybe we can use these forcing constructions to talk about these big objects that we wanted to. Okay.
Could you go back a slide for a moment?
Yes, sure. Okay, cool. So it's the quotient structure. This is going through it a bit quick, just for time reasons. The quotient structure turns out to be the forcing extension of the Boolean ultrapower by the ultrafiltering question. Okay, maybe this gives us a way to interpret it. Problem. No Boolean ultrapower can interpret a generic embedding with a critical point below a measurable cardinal. Very quick and easy to see. Here's your V. If you embed it, well, and be well-founded. So if you embed it into V check U, you know this is an elementary embedding. So this has to be a measurable cardinal. You know that any measurable cardinal preserves V, any measurable cardinal kappa preserves V kappa. So then you know that there's nothing that can be moved down here. So any way you interpret one of these generic embeddings with a small critical point, the ultrapower will go non-well-founded. And that's a problem if you're a universalist, because you want to understand sets. If you're looking for axioms that will settle independent truths for you, you care about the real membership relation. You don't want to look at, some slightly pathological from your perspective relation given by a non-well-founded ultrapower. I do think this does highlight an interesting question for a universalist. Namely, well, what happens if we just look at the embeddings or the generic embeddings where you can do this trick? So generic embeddings with very, very large critical points. And I think there's going to be a talk later on this. So kudos to whoever's giving that talk. So that's just this kind of philosophical upshot. Okay, well, is there a different way of doing this? This would be the next question. And the answer is yes. So you do it via talking about theories and consistency using a lot of class theory. So if you look at bar-wise, and there's also work by Sai and Carolyn and others on this, you can add rules of inference and constants to your language. So stick in a constant symbol for every set in V. Stick in a predicate symbol to denote V itself. And then add the following rules of inference. So if you've got phi of the constant for every B in some set, then infer for all x in that. You can syntactically infer this. And then if you've got phi a bar for all A and V, just infer for all x in V bar phi x. So what you get here are very, very, very big proofs. So these two rules here are going to give you these enormously long proofs. So if you've got a load of phi a's all the way up, when you infer for all x in V bar phi x, you're going to get an infinite, namely proper class-sized proof code. So this is a very strong logic that you can say a lot in. Okay, how are we going to interpret forcing? Well, stick in another constant symbol, W bar, and add into your logic this axiom. So W bar is just a transitive model of ZFC, containing V bar as a subset and with the same ordinals as V bar. And then the consequences of forcing extension can be formulated in terms of the consistency in this very strong logic of these theories where you've added in these new axioms. Now, where do these proof codes appear? So what you have is it turns out, and I'm going to speak from a sort of height potentialist perspective for a minute. You have and you have these proof codes that are sort of these well-founded trees up through V. Then you get to them and you infer something, but this goes beyond the top of V. What it turns out is that these proof codes belong to the least admissible that contains V as an element. So this is the least model of Kripke-Platek theory containing V. Okay? But it's well known that if you have a strong class theory, such as MK, you can code up models of KP. So if we're universists, so we have these proof codes, and these sort of appear in this like quite short extension of V, maybe V plus. Then if we just were universists and had something pretty strong up here, just MK, we can code up these sets above as by talking about classes. And that's just a bit of folklore. If anybody knows the reference for that, I'd be really interested to hear it. But as far as I know, that's just folklore. Okay, so how would this go in the case of, say, the inner model hypothesis or generic embeddings? Well, in a model hypothesis, you can just say, for any way of extending this with an axiom like this that's consistent in this very strong logic, then you will get the truth in a model of that consistent extension. Then it's already true in a model, and that then gives you exactly the consequences in V you wanted for your forcing extensions. So with generic embeddings, if you get a consequence in V from looking at consistency in one of these outer models of an embedding into V bar, then you're going to get the consequences within V. Okay, it's kind of a lot in quick succession, but there's obviously a big hurdle here philosophically. So usually MK is seen as really, really strong for a universalist. And people generally instead opt for a definable formula interpretation of class talk, which will not get you what you want for this sort of construction. And I think it's really thorny, but I don't think it's hugely problematic. I think there can be justifications that you can give, and I'll just gesture towards one. So here's one interpretation people have ascribed to class talk, and this is getting very philosophical now. So consider the sentence, let's start with something a little more basic than ones like that. The rocks rain down. That's something that rocks do collectively, but it's not, the set of rocks isn't involved in any of that. It's just something the rocks do together. And this, a lot of philosophers have seen as indicative of plural quantification as well as singular. So quantification over some things rather than individual objects. Now you can encode a lot of second order content this way. So here's the example, one of the examples Boulos gives in his paper. So there are some gunslingers such that each has shot the right foot of one of the others. Fun fact, if you interpret X has shot the right foot of Y as X equals Y plus 1, you get a sentence that's only satisfiable in a non-standard model of arithmetic, because it gives you some things with an infinite descending sequence. So using this sort of innocent plural talk, you can code up greater than first order content. Similarly, I mean, a lot of people have said, well, this is very nice because you might not think that every plurality forms a set, and then you avoid these problems of proper classes. You can talk about for instance, the Russell class is just the non-self-membered set. The question is, well, what kind of class theory can we get out of this interpretation? I think you can get some non-definable class talk. For instance, there are some sets such that they do not form a set and are also not all and only the satisfiers of a particular first order formula. If you're a universalist who thinks there are already non-definable first order sets, I don't see any reason why you shouldn't think there are that kind of talk, if it's legitimate, gives you non-definable classes as well. Presumably, the classes are at least as rich as the sets in that sense. I think there's other reasons to want to use an interpretation like this from a more second philosophical perspective. So it makes a lot better sense of things like certain kinds of embeddings. So if you have the ordinals as the subset of a model and embed it into V, that can never be first order definable. Similarly, the Kuhnen inconsistency becomes very, very trivial if the embeddings in question are just first order definable. And further still, even if this doesn't get you MK, you only need slightly more than delta 1-1 comprehension to do the work of V-logic. So if you can get just a little bit of strong class theory, then you can get it. Okay, so what have we seen here? I think we've seen there are excellent challenges for the universalist in interpreting forcing extensions. I think there's really good reason for them to actually try and code up this stuff within V for trying to look at new axioms for set theory. But it's possible to do if you have a pretty strong class theory. And I just want to leave you guys with two questions, really. So one, I mean, kind of the shakiest part philosophically of what I've just told you was the justification of class theory. That really needs to be dug into, and we really need to sort of figure out what can we justify if we're going to be universalists? What kind of class theory can you get out of different foundations of such theories? But also, I'd like to think that there's the opportunity to open up the discussion of different kinds of axioms for the universalists. So you're not just limited to the kind of stereotypical programs that you see for universalists, things like fine structure theory, stuff like this, like a lot of the stuff coming out of Wooden's program. Very interesting stuff, but there are also other routes you can go, and I don't think forcing extensions are out. Thanks very much.
Thank you very much. In order to stay synced with the other group, let's say we have one very short question.
26 minutes on this watch, man.
Sorry, Mark.
That's all right.
Yeah, so who has a question? Short one. I have several long questions. Can you start with one question?
Sure. So you're appealing to this sort of idea that you need a class theory Kelvin Morris or something in order to sort of implement your V-logic approach to forcing. But that V-logic approach to forcing is really only into understanding forcing as far as first order is concerned, not producing the forcing extension as a second order model. And so for example, you wouldn't be able to do it again unless you had a Kelly-Morse model after the forcing extension.
Okay, that's really nice.
So what do you think about? I mean, do you want to understand your approach to forcing as a second order forcing?
Yeah. So what I'd really like to have is just kind of complete freedom for the universalist, that they can just look at whatever you can dream up just as much as a multiversist can. That's a really good question, though. I haven't thought about. I haven't thought about that actually in the what goes on with the second order theory and the forcing extension. So I'll have to check that out. I mean, I guess you can look at it different ways, right? So I'd like it to be total freedom, but equally, if it comes with some restrictions, that's an interesting thing to study for the purposes of filling out the universalist position. So I'm kind of open to looking at both ways there, but thanks.
Yeah, I'm afraid we have to start this official, we have to stop this discussion now because we have to start the next talk. Thank you very much.
Yeah, thank you.